It is also possible to use average growth rates to make estimates beyond the limits of available data and thus to forecast trends. This process is called extrapolation. Example 10. Extrapolate beyond the limits of the table of SARS cases to estimate the number of cases on April 16th and April 30th. Extrapolation is similar to interpolation, except for the fact that it is impossible to find data points close to and surrounding the data value we wish to estimate. This is because the data point we wish to estimate is beyond the limits of the available data. Instead, we will do the next best thing and use data points close to but less than the data point we wish to estimate. In our case, we wish to estimate the number of SARS cases on April 16th, so we will find the average growth rate using the April 10 and April 15 data points. Recall, the average growth rate between April 10th and April 15th can be found by the following formula: change in function value divided by change in independent variable. Remember, the function value is another name for the values corresponding to the dependent variable. In this case, the dependent variable, the variable we really care about, is the number of SARS cases. The independent variable is the variable the dependent variable depends on. That's the date. So to find the change in the function value from April 10th to April 15th, we will subtract the number of SARS cases on April 15th by the number of SARS cases on April 10th. That is 3,235 cases minus 2,781 cases. To find the change in the independent variable, we will determine how many days went by between April 10th and April 15th. 15 minus 10 is 5. 5 days went by. 3,235 minus 2,781 equals 454. So 454 new cases occurred in these 5 days. We use sharing division to share those 454 cases evenly among those 5 days. The result is 90.8 new cases per day. Now, if I assume the growth rate is constant, I could start with my 2,781 cases on April 10th and add 90.8 cases each day until I get to 3,235 cases that marks April 15th. The idea behind extrapolation is to assume that this growth rate will remain constant indefinitely. That is, we will assume that the number of SARS cases continues to increase by an average of 90.8 cases per day. We can estimate the cumulative number of cases on April 16th as 3,235, the number of cases on April 15th, plus 1 times 90.8. We'll add 90.8 to 3,235 one time. We get 3,325.8. And since this is the end of the problem, we will round that to 3,326 cases. That is, as of April 16th, we speculate that there was around 3,326 total cases of SARS. Similarly, we can estimate the number of cases on April 30th as 3,235, that is the number of cases on April 15th, plus 15 times 90.8. We get this 15 because April 30th minus April 15th is 15 days. That is, 15 days went by since there were 3,235 cases. And since we are assuming we are increasing the number of cases by 90.8 every day. We should add 15 times 90.8 to the number of cases we had on April 15th. We get 4,597 cases. So, if the number of new cases per day stays relatively the same, we will have around 4,597 SARS cases as of April 30th. Note, the actual number of SARS cases on April 30th, as reported by the World Health Organization, was 5,663. How does this compare to our estimate? Notice the actual number is over our estimate. That is, our estimate was an underestimate. This means the average growth rate per day from April 15th to April 30th was actually greater than 90.8 cases per day. This example illustrates why one should be cautious in using extrapolation to make estimates well beyond the limits of data. In the table below, we summarize the process of extrapolation. If we want to extrapolate to estimate the function value corresponding to x sub 3, we should do the following. Step 1. Find data values close to x sub 3 in which we have information about. For our generalization, we are assuming that we know the dependent variable value for x sub 1 and for x sub 2. And we are assuming both x sub 1 and x sub 2 are less than x sub 3. Step 2. Find the average growth rate between x sub 1 and x sub 2. Remember, to do this, we will find the change in the function value, or the dependent variable, and divide that by the change in the independent variable. Step 3. Estimate the function value corresponding to x sub 3 as y sub 2 plus x sub 3 minus x sub 2 multiplied by the average growth rate. That is, we want to begin with y sub 2, the function value that corresponds to the independent variable value that is closest to the data point we wish to make an estimate about. Then we consider how far away x sub 3 is from x sub 2. That tells us how many times we need to add the average growth rate. Summary. A data table shows a relationship between two quantities. We designate one quantity as the independent variable. If time is involved, the independent variable is almost definitely time. And think of the other quantity, the dependent variable, as a function of the independent variable. 2. Percentage change can provide information that may not be readily apparent from the raw data. We calculate percentage change from one function value to another using this formula. Percentage change equals change in function value divided by previous function value. Number 3. The average growth rate of a function over an interval is calculated using this formula. Change in function value divided by change in independent variable. Notice the numerators for both percentage change and average growth rate are the same. Number 4. To make an estimate by interpolation or extrapolation from a function value, multiply the average growth rate by the number of increments in the independent variable, and then add the result to the function value. Number 5. At best, interpolation and extrapolation give estimates. They are most reliable over short intervals.